this video, we discuss singular Sturm-Liouville problems, but we're going to start by reviewing eigenvalue problems in general and regular Sturm-Liouville problems. And then once we've reviewed all of the necessary prerequisites, then we will define singular Sturm-Liouville problems. And then we'll look at an example. We're not actually going to solve that example. We're just going to show that the operator featured in the differential equations acting on the space of functions that may satisfy the differential equations in the corresponding boundary conditions is symmetric. So we're going to do all of that after we have done this review and defined singular Sturm-Liouville problems. Okay, so remember in the other videos, we've talked about this before. If we have a linear operator, L, and it's a differential operator, and it's acting on a space of functions, chi, and those functions are defined on the interval from A to B. If the problem looks like this, so you take the operator, apply it to F, so you're gonna have some linear combination of the derivatives of F and F itself over here, plus a constant lambda, that's a real parameter, times sigma of x times f of x equals 0, a differential equation that looks like this for x between a and b, where lambda is a real parameter and sigma is a given function, and that sigma function is always positive on the interval from a to b. That is called an eigenvalue problem. Excuse me. Now, the linear operator will be given to you. This function sigma is either given to you or can be found through algebraic manipulation to write the differential equation in this form. But everything is given except for the function f, or everything is either given or can be found except for the function f and the parameter lambda. Now, these values of lambda that give us non-zero solutions to this differential equation are called eigenvalues for this particular differential equation. And the corresponding functions, the functions that go with those values of lambda, those non-zero solutions to the differential equation, those are called eigenfunctions. So we're looking for a set of functions that satisfy the differential equation for certain values of the parameter lambda, and lambda is just a real number in our case. Okay, so that is an eigenvalue problem in general. Now, a regular Sturm-Liouville problem is defined in the following way. If we have a finite interval AB, and the functions p, q, and sigma are all real valued functions, and kappa 1, kappa 2, kappa 3, and kappa 4 are real numbers, and the function p is continuously differentiable on the interval from a to b. So you can take its derivative, and the derivative is continuous, and the function is positive for all x in the interval from a to b, closed interval. So it's positive all the time for the interval of interest. And q and sigma are continuous on the interval from a to b. And sigma is positive for all x values in that interval. And kappa 1 and kappa 2 are not both 0. And kappa 3 and kappa 4 are not both 0. Then this boundary value problem, which is a special form of that eigenvalue problem from before. Remember, the eigenvalue problem from before was some linear differential operator applied to f plus lambda times sigma times f equals 0 for x on the interval from a to b. That's an eigenvalue problem, or the differential equation that you would see in an eigenvalue problem. So this boundary value problem, where that linear operator applied to f is actually the operator given by p times f prime, take that product, take its derivative, then add q times f. When that is our linear operator, we call this a regular Sturm-Liouville problem, provided that that's the differential equation and we've got these two boundary conditions. Now, remember what we said earlier, p is just some function that's positive on the closed interval from a to b. Sigma is a function that is positive on the closed interval from a to b. Q and sigma are continuous on the interval of interest. And this kappa 1, kappa 2 not being both 0 at the same time just tells us that this first boundary condition actually tells us something. Now, I want you to notice that this first boundary condition deals with f of a and f prime of a, and we're talking about this interval from x equals a to x equals b. So our concern is for functions defined on this interval from A to B, and we want the differential equation to be satisfied on the interior of that interval. This first initial condition, or excuse me, this first boundary condition deals with the left endpoint. It says at x equals a, this is how f of a and f prime of a have to be related to each other. Now, if kappa 1 and kappa 2 are both 0, then this would just say 0 equals 0, which wouldn't tell us anything. So that's an important condition. If kappa 3 and kappa 4 are not both 0, or if they are both 0, then this would just say 0 equals 0. It also wouldn't tell us anything. So I want you to notice that the first boundary condition tells you about the relationship between f of a and f prime of a at the left endpoint, or the function, excuse me, the function at the left endpoint, because we're dealing with f at a and its derivative at a. The second boundary condition deals with the function and its derivative at the right endpoint. So we've got this differential equation, which is just the special case of that eigenvalue, the differential equation that you would see in an eigenvalue problem. And we've got two boundary conditions like this that deal with the relationship between the function and its derivative at the left endpoint and the function and its derivative at the right endpoint. Then we have what's called a regular Sturm-Liouville eigenvalue problem. Now, there are a couple of things that we should discuss about the solutions to those problems, and they all have to do with that operator L that we saw on the left-hand side of the differential equation. Now, this is a fact. It's stated in the textbook. It says that if chi is a space of functions that are twice continuously differentiable, so you can take the derivative twice, and that satisfy the differential or satisfy the boundary conditions in our boundary value problem in that regular Sturm-Liouville problem, then the operator on that left-hand side, that p times f prime plus q times f, that's what we get when we apply that linear operator to L, or excuse me, apply that linear operator L to f. That operator is symmetric on chi. So that's saying the following. That's very important. It's important that that operator be symmetric because of a theorem that we get as a result of that operator being symmetric. But before we do that, let's just remind ourselves what it means for an operator to be symmetric. If a linear differential operator L acting on the space of functions chi, where those functions are all defined on some interval I, if we have something like that, we call that differential operator symmetric on chi if the following is true. I want you to notice what we're doing here. We're integrating over the interval of interest. And this says, take one of the functions and then multiply by the linear operator applied to the other function. Then do it the other way around. Take the second function and multiply by the linear operator applied to the first function. If you subtract those and you integrate, you're going to get 0 for any f1 and f2 in that space of functions chi. And remember, chi for these problems is the space of functions that might satisfy the boundary value problem. So those are functions that are twice continuously differentiable, so you can take their second derivative. These are the functions f. This is the space of functions. Chi is where we're going to find our solutions to the differential equation subject to those boundary conditions. Excuse me. So if our operator is symmetric on the space of functions that might satisfy the differential equation subject to the boundary conditions, which means this, then the following is true. And this is really important. This is what we want. When we are solving an eigenvalue problem, we want that operator to be symmetric, because this theorem says that if the operator in the eigenvalue problem is symmetric, then the following is true. All the eigenvalues, remember those are values of the parameter that have non-zero solutions to this differential equation, or that correspond to non-zero solutions of this differential equation. Those are all real. And the eigenvalues form an infinite sequence, and it's increasing. So you have one lambda, and then you have another one that's larger, and another one that's larger, and that keeps going. And as n goes to infinity, the lambdas go to infinity. Rather than just writing lambda, we write them with subscript because there are infinitely many of them. It makes sense to add that subscript lambda sub n. That's the first one, that's the second one, that's the nth one, and so on. So we've got an infinite sequence of eigenvalues, and they go to infinity as n goes to infinity. and then the eigenfunctions associated with the distinct eigenvalues. So we've got infinitely many eigenvalues. That means we're going to have infinitely many eigenfunctions as well, are orthogonal with weight sigma, and that sigma is the same sigma from the differential equation in our regular Sturm-Liouville problem setup. Those functions are orthogonal with weight sigma on the interval from A to B. And just as a reminder, this is what it means for our functions to be orthogonal. If we have that function, sigma, it's defined on some interval I and it's positive for all x in the interval, then we say that two functions, also defined on I, are orthogonal with weight sigma if the following is true. You multiply them together, you multiply by sigma, you integrate over I. If you get 0, we say that those two functions are orthogonal with that weight. Now, if that weight is 1, if sigma of x is just the function y equals 1, pretty boring function, then you just have the integral of this product is 0. F1 times F2 is going to be 0. If this is true for any two distinct functions in a set, we say that the set of functions is orthogonal. So this means that when we're solving a regular Sturm-Liouville problem, which looks like this, it's a boundary value problem. What we're looking for are two things. We want the functions that satisfy this differential equation and the boundary conditions at the same time. Those functions are called the eigenfunctions of the boundary value problem. And of course, we're talking about non-zero functions. And we also want the corresponding values of this parameter, lambda. Those are called the eigenvalues. So we want the eigenvalues and the eigenfunctions. If you plug in the eigenvalue and the corresponding eigenfunction to this differential equation, you do all of the calculus, you simplify, doing some algebra, you're going to get 0. So those functions and eigenvalues satisfy this differential equation, and the functions themselves will also satisfy these two boundary conditions. That's what we're looking for. When we solve this problem, we want the eigenvalues and the eigenfunctions. Now that's a review of regular Sturm-Liouville problems. And again, remember, the eigenfunctions and eigenvalues that we're looking for satisfy theorem 3.8 because this operator L in the eigenvalue problem is symmetric. That's what we're looking for. But now let's talk about singular Sturm-Liouville problems. This is definition 3.27 from the Constanda differential equations text. It's Solution Techniques for Elementary Partial Differential Equations, 2nd edition by Christian Constanda. It says this: an eigenvalue problem consisting of this equation, P times F prime plus QF plus lambda times sigma times F equals 0 for x between A and B. So it's the same differential equation in our regular Sturm-Liouville problem. This is an eigenvalue problem consisting of this equation and boundary conditions. It is called a singular Sturm-Liouville problem. If one of the following is true. So either P of A is 0 or P of B is 0 or both. Or any of P, Q, and lambda, or excuse me, and sigma becomes infinite as x approaches A from the right, or as x approaches B from the left, or both. Remember that little plus sign means we're approaching from the right. So that means for values great from the side where values are greater than A. This little minus sign means we're approaching from the left. That means for values of X that are less than B, or both. Or if the following is true, if the interval of interest, the interval from A to B, is not a finite interval. So it might be infinite at X equals A, or at B, the left side, or both. So that's a singular Sturm-Liouville problem. Now I just want to go over these conditions again, just for emphasis. This first condition says that we have a singular Sturm-Liouville problem rather than a regular Sturm-Liouville problem if this function P, which was supposed to be positive all the time in the regular Sturm-Liouville problem, are positive on the interval from A to B, including A and B. If that function that's multiplying f prime is 0 at X equals A, that's the left endpoint of our interval, or it's 0 at the right endpoint of our interval, or it's 0 at both endpoints of our interval. In that case, we have what's called a singular Sturm-Liouville problem. I think that we all probably have an intuition that that's going to be an issue, because if the function multiplying f prime here is 0 at an endpoint, well, if it's 0, then that term involving the derivative is gone. We don't even have a differential equation anymore at that x value. So there's something a little bit funny about that. Whenever that happens, when the derivative disappears from your differential equation, that's a sign that maybe something is wrong. Or maybe you have what's called a singular Sturm-Liouville problem, which needs to be handled differently. That happens with a lot of singular types of problems. Okay, so if one of those, or if the function is 0 here, or both, we've got a singular problem. Or if P, the function multiplying f prime before we take its derivative, before we take the derivative of that product, or Q, or sigma, becomes infinite as X approaches A from the right. So this is our interval of X values. And we're approaching A from the right. So from the interior of that interval. If one of those functions goes to infinity or negative infinity, as X approaches A from the right, then we have a singular Sturm-Liouville problem. Or if one of those functions goes to positive or negative infinity as X approaches B from the left, so also from the interior of the interval over here, or both. If any one of those three functions goes to plus or minus infinity as we approach A from this side, or B from this side, or both, then we have a singular Sturm-Liouville problem. Or if the interval itself doesn't look like this, if the interval itself is infinite, so the possibilities here are, our interval might be from negative infinity to B, or our interval might be from A to infinity, or our interval might be from negative infinity to infinity. In any one of those cases, well, we've got a different type of problem than we have with our regular Sturm-Liouville problem. Things need to be handled differently. So this is a singular Sturm-Liouville problem. Now our goal is still to find all of the functions that satisfy this differential equation. Those are called the eigenfunctions, and the corresponding values of the parameter lambda that go with those functions, those corresponding values are called the eigenvalues. But of course, we're not just dealing with this differential equation, we're also dealing with some boundary conditions. And again, we want to have this operator here. This is L applied to F. We want the operator L to be symmetric on the space of functions that might satisfy this differential equation and the boundary conditions. Because if it's symmetric, then we get all of the results of theorem 3.8 for free. So we want that operator to be symmetric on the space of functions that might satisfy this differential equation. So they have to be twice continuously differentiable functions. And they also need to be a space of functions that satisfy the boundary conditions. So we're still looking for eigenvalues and eigenfunctions, but things are a little funny at the left endpoint or the right endpoint or both, either because of the nature of the interval itself or because of the functions in our differential equation. But we still want to find the same things. And we want the operator L in the differential equation on the space of functions we're interested in to be symmetric. So let's write this down. Let's say we need to choose boundary conditions to ensure that the operator L, where L applied to F is P F prime prime plus QF, we want to choose the boundary conditions to ensure that that operator remains symmetric. On the space of functions that may satisfy the differential equation and the boundary conditions that we're interested in. We want that operator to be symmetric so that we know we'll have infinitely many eigenvalues forming an infinite sequence that's increasing. The eigenvalues will go to infinity as n goes to infinity. And the eigenfunctions that go with those eigenvalues, we want them to be orthogonal with weight sigma on the interval of interest. In order for all of this to happen, we need the operator to be symmetric. And again, the operator is not just symmetric by itself, it's symmetric on a space of functions. So we want that operator to behave like this. We want this to be true for any F1, F2 in that space of functions. If we plug in our operator here and we simplify this integral, we want to get 0 every time for any two functions in the space of functions that are twice continuously differentiable and satisfy our boundary conditions. Now, often what we need to ensure that that operator is symmetric is that the function and its derivative remain bounded as we approach x equals a from the right, or as we approach x equals b from the left, or as x goes to negative infinity, or as x goes to positive infinity, or both. If that function remains, or if the function and its derivative remain bounded at x as we approach the left endpoint or the right endpoint of our interval, whether that endpoint is a finite number or we're going out to negative infinity or going out to positive infinity. If that remains bounded, then the operator L is often symmetric on the space of functions that we're interested in. So let's write that down. Say often L is symmetric on the space of functions that we're looking for, or the space of functions that contain the functions that we're looking for, if f and f prime are bounded as x approaches a from the right, or f and f prime are bounded as x approaches b from the left, or f and f prime are bounded as x approaches infinity, or f and f prime are bounded as x goes to negative infinity, excuse me. And of course, this depends on the nature of the interval that we're interested in. If the endpoints are plus or minus infinity, one or both of those is infinite, we're going to need a condition like this. If one of these other issues, or if we have one of these other issues where P of A is 0 or P of B is 0, so we have a 0 multiplying that F double prime at some point, or actually, well, you know, we have a 0 multiplying that F prime before we take the derivative at the left endpoint or the right endpoint. If they're 0, or if any one of these functions, P, Q, or sigma, blows up, meaning it goes to positive or negative infinity as we approach the left endpoint or right endpoint. Often, as long as the function and its derivative are bounded as we approach that left endpoint or right endpoint from the interior of the interval that we're interested in, then our operator is symmetric, and because our operator is symmetric, we get all the things that we want. So then we have a well-posed singular Sturm-Liouville eigenvalue problem. And when we solve that well-posed singular Sturm-Liouville eigenvalue problem, we'll be able to find this infinite sequence of eigenvalues that go to infinity as n goes to infinity, and the corresponding eigenfunctions. Those are solutions, non-zero solutions to the differential equation that are orthogonal with weight sigma, where sigma is that function from our differential equation. So let's look at an example. Not actually going to solve this example, but we are going to show that the operator in the example is symmetric on the space of functions defined or implied by the boundary conditions. So here's a singular Sturm-Liouville problem. Got x squared plus 1 times f double prime plus 2x times f prime plus lambda minus x times f equals 0 for x greater than 1. And right away, I want you to notice we're talking about an interval that looks like this. We start at 1 and we go to infinity. So we've got an infinite interval of interest. Now, normally, when we're dealing with a regular Sturm-Liouville problem, we've got boundary conditions that specify the relationship between f and its derivative at the left endpoint and the right endpoint. Now, we only really have a left endpoint here. So we're still going to have this first boundary condition. In our case, we're given that f prime of 1 is equal to 0. Okay, so they're telling us something about what happens on the left. And then they can't really tell us a function value on the right, but we could require this to be true, and that is the second boundary condition. We want f and f prime to be bounded as x goes to infinity. So this is a regular Sturm-Liouville problem. I want you to notice too that this x squared plus 1 times f double prime plus 2x times f prime is the result of a product rule. That's going to be the same as the derivative with respect to x of x squared plus 1 times f prime. And if you're not sure, you can check. This is your first function, and that's your second function. You've got your first function here times the derivative of the second plus the second function times the derivative of the first. Now, if you're saying to yourself, why is that important? It's because that means I can write the differential equation this way. Now, rather than using this Leibniz operator notation, we can use this notation, the prime notation that was used in the earlier version of the problem statement. I've got x squared plus 1 times f prime plus, looks like here I've got a negative x times f and a lambda times f if I distribute. I've got that. And I'm going to use the abbreviation BDD for bounded. Now it's looking closer to this, I can see that my P of X is X squared plus 1, and X squared plus 1 is clearly positive all the time, and it's definitely positive for X between 1 and infinity. It's positive for all real numbers anyway. So that's our P. Now, if we're looking at this in pattern matching, Q is a function that's multiplying F that does not have an extra lambda multiplying it. So this is my Q. And the lambda times sigma times F is right there. It's that term. So it looks like sigma of X is equal to 1. Sigma is positive, P of X is positive all the time. And even though I've got this QF and lambda F in the reverse order, we can see that this is in the form of the differential equation that we see in our Sturm-Liouville problems. So this is truly a Sturm-Liouville problem, but we've got an infinite interval of interest. So that means we've got a singular Sturm-Liouville problem. I've got two boundary conditions, one specifying what happens on the left, one specifying what happens on the right. This one on the left is just like a regular boundary condition. So like this first boundary condition from the regular Sturm-Liouville problem. And this condition on the right deals with what happens as X goes to infinity. Okay, so that is our differential equation. I'm going to rewrite it one more time so it has the exact form that we want. Let's do this. This right here is our operator L. L applied to F is P times F prime prime plus Q times F. In this case, P of X is X squared plus 1 and Q is negative X. So this, we can see now, fits that form of a singular Sturm-Liouville problem exactly. Now someone might ask you to show that the operator L in the singular Sturm-Liouville problem above is symmetric on the space chi of twice differentiable functions. We want to be able to take that second derivative of F. That satisfy the boundary conditions in the problem. Okay, now remember what it means for an operator to be symmetric. We want to let F1 and F2 be members of that space of functions chi, twice differentiable functions that satisfy these boundary conditions. F prime of 1 is 0, and F prime are bounded as X goes to infinity. And then we want to look at this integral. It's the integral over I of F1 times the linear operator applied to F2 minus F2 times the linear operator that we're interested in applied to F1. If this expression is 0, then the operator in our question, or the operator in our singular Sturm-Liouville problem, is a symmetric operator on the space of functions that we're interested in. And that means that when we do solve this problem, we can expect infinitely many eigenvalues that are increasing as n goes to infinity. They go to infinity, and corresponding eigenfunctions that are mutually orthogonal, which is pretty nice. So the interval of interest is 1 to infinity. And our linear operator is this. We take the function, we take its derivative, and then we take the derivative, or we multiply it by x squared plus 1, and then we take the derivative of that and we subtract x times the function. I want that operator applied to f2. So we're going to have x squared plus 1 times f sub 2 prime. I want the derivative of that minus x times f sub 2. A lot of parentheses there. Yep, I think that's good. Those parentheses apply to that, and then we take the derivative, and then those parentheses on the outside apply to that. Good. And then we want pretty much the same thing, but you're going to switch your f1 and your f2. Want to evaluate the integral of, or that integral, excuse me, if we get 0 for any two functions f1 and f2 that are twice differentiable and satisfy the boundary conditions, then we're good to go. Then our operator is symmetric, and that means we're going to get the types of solutions, eigenfunctions, that we're looking for that correspond to the types of eigenvalues, those lambdas that we're looking for. Let's work this out. Again, if I use the product rule here, it's my first function and there's my second function. We'll have this derivative of the first times the second plus derivative of the second times the first I'll just put a dx on that. Write this as a separate integral. Same over here. Derivative of the first times the second plus derivative of the second times the first. No big deal. Just a little Calc 1 product rule stuff. Okay. Oops, that should be an F1. And if we want now, we can distribute this F1 to everything here and here. I'm just simplifying the integrand now. Got 2x, f sub 2 prime plus x squared plus 1 times f sub 2 double prime. All of that, I'm distributing that f1 to it. I'll take that and I'll multiply by f1. And then here I'll have minus the integral from 1 to infinity of x times f1 times f2 dx. Okay, now here I will distribute the negative and the f2. So I'll have a negative integral from 1 to infinity of, and again, I'm going to keep this all grouped together. Just rewriting it. Writing that in the reverse order, just because I want to. Oops, there should be a dx there. And now when I distribute a negative f2 to this, I'll have a positive integral from 1 to infinity of x times f1 times f2 dx. And now we see that this reduces with this. That's going to happen with your q times f2 and your q times f1 every time whenever you're checking the properties of this, a linear operator from the Sturm-Liouville problem. Okay, so now we've got this integral. The integral from 1 to infinity of 2x f2 prime plus x squared plus 1 times f sub 2 double prime times f1 minus something that looks very similar, but with the subscripts switched. Alrighty. Now I want you to notice that this is actually an expanded form from a product rule. I expanded it earlier, but perhaps I shouldn't have. Let's write it as this again. It's the derivative of x squared plus 1 times f sub 2 prime prime. And similarly, this is the derivative of x squared plus 1 times f sub 1 prime prime. Now, we might want to write this differently. We might want to write it with the f prime being primed somehow. So I want you to notice the relationship between this right here and the derivative of the product this times this times this. So I'm going to take x squared plus 1 and my f sub 2 prime, which are already in parentheses. We're going to take the derivative of that, and I want to multiply by f1. I want to take the derivative of this. Now, I'm going to think of this as my first function, and this is my second function. So when I take the derivative using the product rule, I get derivative of the first times the second plus derivative of the second times the first. Now, this is what we have right here. So if I wanted to, I could take this expression and substitute this product prime minus this. And that's exactly what I'm going to do. So I know that this is true due to the product rule, and that means that this highlighted expression is equal to f1 times x squared plus 1 times f sub 2 prime prime minus, I'll factor out that polynomial, x squared plus 1 times f sub 1 prime times f sub 2 prime. Okay, so that we're going to take this guy and we're going to replace it with this. And that's nice because once I've got a whole expression and I'm taking the derivative of that, and then I take the antiderivative, that whole expression is going to, or that derivative will just disappear when we do the antidifferentiation. And of course, this looks very similar, but with the opposite subscripts. Instead of an F1, we've got an F2, or instead of an F2 here, we've got an F1. Instead of an F1, we've got an F2. So we can make the same substitution over here, just flip the subscripts. Oops. So we've got this. Excuse me, the integral from 1 to infinity of f sub 1 times x squared plus 1 times f sub 2 prime prime minus x squared plus 1 times f1 prime times f2 prime. And then we're subtracting something that looks very similar to this, but with f1 and f2 prime flipped. We're subtracting the integral from 1 to infinity of f sub 2 times x squared plus 1 times f sub 1 prime prime. And then we're subtracting a negative there. So I guess we could put a dx on this and write an integral from 1 to infinity there as well. Subtracting a negative would give us a positive integral from 1 to infinity of x squared plus 1 times f sub 2 prime f sub 1 prime dx, just changing the subscripts. But notice this expression is exactly the same as that expression, they just had opposite signs. So those are gone. Oops, and I'm missing a dx. So the only thing we have here is the integral from 1 to infinity of this expression, f sub 1 times x squared plus 1 times f sub 2 prime prime minus f sub 2 times x squared plus 1 times f sub 1 prime prime. And because of the way derivatives work, of course, we could take that and write it as a single derivative. Okay. All right. Now, We know from calculus 2 that every improper integral is actually the limit of a proper integral. So I'll take the limit as b goes to infinity of the integral from 1 to b of this. And I think I'm going to factor out that x squared plus 1 as well. We've got x squared plus 1 times f1 times f2 prime minus f2 times f sub 1 prime. Derivative of that. And the antiderivative of the derivative is just the function itself. So when I anti-differentiate this, I'm just going to get that. Oops, we evaluate at 1 and b and we subtract. That's what we get when we evaluate at b. When we substitute in 1, we'll get this, and I run out of space, so I'll just write it on another line. I'm subtracting the limit as b goes to infinity of this expression evaluated as x equals 1. 1 squared plus 1 is just 2. And remember our boundary conditions. We're trying to show that the operator in this particular singular Sturm-Liouville problem is symmetric on the space of functions that are twice differentiable and satisfy the boundary conditions. So for each of these functions, f1 and f2, when we plug in 1 to the derivative, we get 0. So f prime of 2 at x equals 1 is 0, and f prime of 1 at x equals 1 is 0. So this is 0 minus 0. Of course, the limit of 0 is 0. So this piece is gone. And the only part that we need to concern ourselves with is what we have right here. So I have the limit as b goes to infinity of b squared plus 1 times this expression and honestly, I'm a little concerned because if the function itself is bounded as x goes to infinity and f prime is bounded as x goes to infinity, this is just some finite number times a finite number. And over here, I've got a finite number times a finite number as well. So this in general is just some finite number times b squared plus 1. And if this number is not 0 and I multiply by b squared plus 1, I'm going to get plus or minus infinity. If this number is negative, I'm going to get negative infinity. If this number is positive, I'm going to get positive infinity. The only way that I'll get 0 from this, and I need to get 0 for this in order for my operator to be symmetric, is if this is equal to 0. So I would need this relationship to hold. Now, I think I can get that to happen if I add a well-chosen 0 here. Notice that I've got an f sub 2 prime multiplying f1 and an f sub 2 multiplying f sub 1 prime. So if I wanted to, I might just add and subtract f sub 2 at b and f sub 2 multiplied by f sub 2 prime at b. That might help. Adding it and subtracting is just adding a well-chosen 0. Then I could regroup these guys and regroup these guys. And then say, okay, these have an f sub 2 prime at B in common. And these two have an f sub 2 of B in common. Okay, now it's a little different. It's organized a little differently. Now I've got f sub 2 prime at B. Since f prime is bounded, we know this is just some number. F is bounded as well, so f of B or f sub 2 of B is just some number. And it's multiplied by this difference. I want you to notice that it's the difference between two functions. We're not taking the derivative. I want f sub 1 of B, and I'm subtracting f sub 2 at B. And here, I'm doing the same thing, but with the derivatives. So through this, adding a well-chosen 0 and then reorganizing, I have this expression that's multiplying as b squared plus 1 in this form. And this is going to be 0, and this is going to be 0, provided that those functions, f1 and f2, that are in the space of functions that we're interested in, the space of functions that satisfy f prime of 1 is equal to 0, and f prime are both bounded as x goes to infinity. As long as those functions all have the same bound, so let's say this goes to 17 as b goes to infinity, and so does this, or this goes to 20 as b goes to infinity, and so does this. As long as those have the same bound, we're good. So that means that my operator L is symmetric. Excuse me, provided all functions f in chi, excuse me, have the same, let's say limit rather than saying bound, because we can bound functions in lots of ways. We're interested in the smallest one. I'm not going to get into that too much. Let's say that they have the same limit as b goes to infinity. And their derivatives have the same limit as b goes to infinity. If that's true, then we're good to go. And our operator is symmetric. And that means not only do we have a singular Sturm-Liouville problem, but we have a singular Sturm-Liouville problem in which the linear operator is symmetric on the space of functions we're interested in. And therefore, when we try to solve this problem, we're guaranteed to have an infinite increasing sequence of eigenvalues that go to infinity as n goes to infinity, and corresponding eigenfunctions. Those are still functions that solve this differential equation for given values of that, or for specific values of that parameter lambda, specific values or specific eigenvalues. Those functions are going to be pairwise orthogonal with weight 1, just orthogonal, because sigma is equal to 1 in this particular differential equation. So I hope that helps. Sorry we didn't actually solve one yet, but I hope you'll understand why these boundary conditions are necessary. And again, it's because we want the eigenvalues and the eigenfunctions to have the properties that we want.